No further ado, Scott Ford, in from Richmond, Virginia, is going to be going over some metrics, important metrics for DevOps. Working in the DevOps space is actually something that is of great interest to me. So, take it away. Thanks.
Thanks so much for having me. Who else enjoying the conference so far?
All right.
Nice. Thanks to the organizers and all the hard work that they're doing. How many people in this room identify as a software developer? Okay. And of those of you, how many of you like working on something that someone else has put together or that you've inherited from others? 1, 2, 3. Okay, I ask this every time I give a talk, and that's really consistent. So that's my passion, is cleaning up other people's messes. I really enjoy taking systems that other people have built and making them better. And this talk is part of the kind of philosophy that I've developed in terms of like digging into a system and looking at what you can glean from metrics to help you figure out, where you should target and how you can start making some traction on making that system better. So who here's been to a doctor before? I assume everybody. So what are some metrics that your doctor uses when you go to the doctor's office? You just shout some out? Blood pressure. Weight. Pulse. Temperature. All right, these are all good ones. So we got age, weight, height, temperature, your blood oxygen saturation level, and blood pressure. Of those metrics that your doctor uses, your doctor doesn't use any one of those metrics in complete isolation from the others. Your doctor looks at all those metrics and others, not just those, but lots of others, in collection to kind of tell a story about your entire health. And that's a large part of what we need to do when we're working on software systems as well, is when we're looking at metrics and collecting metrics from our software systems, we need to think about how all of those metrics can be used together. Each one can provide some hints about where to look. So if you're overweight, for instance, that might provide some hints or create some extra urgency for getting some other metrics addressed. So like if your blood pressure is really high and you're overweight, that might send some alarm bells off for your doctor. So this is me. This is my face. I'm the co-founder and chief code whisperer at Corgi Bytes, where we focus on improving legacy systems. We don't build anything from scratch. We only like to take what other people have created and use that as a starting point. As part of that, we perform what we call code inspections. And this is us taking a really deep dive into a software system and figuring out where improvements can be made, what kind of makes it tick, what are the trouble spots, of that sort. We've looked at a lot of different projects over the years, and we've gained some pretty strong opinions about what good metrics, what are the important metrics to look at. So that's what we're going to talk about today, is what metrics are important, how you can collect those metrics, why you should collect those metrics, and then for those metrics, like what are some good values, how are those metrics used together, and then we're gonna end by looking at some common scenarios for what different good and bad values in combination might be able to tell you about your system. So first, what metrics should we look at? So there are 3 that I'm going to cover in this talk that we rely on pretty heavily. First is churn. This is a measure of how your system is changing. So how the files in your system are changing and what that can tell you. Oh, I gave that away. So churn for any specific file in your system is how many times that file has changed throughout the life of your application. This is gleaned from your source code repository. So if you're using Git, this is really easy to capture. You can still get this from other source code systems as well. But in general, on a file-by-file basis, how many times across the life of your application has that file changed? And this can be broken into 2 categories. You've got the lifetime churn, which is throughout the entire life of your project. But perhaps more importantly, is recent churn. Because when you're looking to make improvements in your system, what's changed recently can provide more insights into what might change in the future. Next up is code coverage. So code coverage is a measure of how much of your code base is executed when your test suite runs. And there are different types. I like to look at code coverage not just for your entire suite or not just for unit tests, but also the different kinds of tests that you have in your system. So if you have acceptance tests, consider your acceptance test coverage. If you have integration tests, consider your integration test coverage. And if you have unit tests, consider your unit test code coverage. And if you have a well-balanced pyramid, test pyramid, then your unit test coverage should be a lot higher than your integration test coverage, and your integration test coverage should be a lot higher than your acceptance test coverage. And that's one way that you can measure and try to get some insight into how well balanced your test suite is. If you have too many acceptance tests, then you may have a test suite that's taking several hours to build or several hours to run, and creating frustration and then generating, encouraging bad habits for the developers in your team. Next up, we have complexity. So complexity is a measure of how difficult a chunk of code is to work with. So how hard is it for people in your team to make changes to a block of code? What's the risk that they're going to introduce a bug when they make a change to it? And complexity comes in a lot of different flavors. My favorite is cyclomatic complexity, which is a measure of the number of unique paths to a particular chunk of code. This also ends up becoming a pretty good stand-in for the number of tests that you have to write to get 100% code coverage when looking at a statement-by-statement code coverage analysis. There are a lot of critics of cyclomatic complexity. SonarQube has done some work, and they've put a proposal forward for cognitive complexity. They have a really good white paper out that I encourage you to take a peek at if you're interested. And it's meant to be a measure of the cognitive effort required to understand a block of code. So, which is a little bit different than cyclomatic complexity, which is the number of independent code paths. One of the advantages for cognitive complexity over cyclomatic complexity is it can give you a pretty good aggregate count of how complicated your system is as a whole. Cyclomatic complexity, because of the way it works at a method by method level, it's much harder for you to get a sense of that, how complicated your system is as a whole in aggregate. At best, you can usually get a sense of how complicated the individual components that make up your system are. So that's one of the advantages of using cognitive complexity. There are other kinds of complexity that you can look at as well that I didn't include in this slide deck, but they are definitely out there. So next up, how do we collect all these metrics? For churn, there's a really good script that you can plug into your Git tool chain if you're using Git. It's available at the URL on the screen. You can just stick it into your path, and then whenever you run git churn, it will give you a nice little output of the number of files, the number of times each file has changed, and it's sorted in reverse order, so you see the file that's changed the most at the top. Code coverage. To collect this, you need to use a code coverage collection tool. These are going to vary by language. At Query Bytes, we take a very language-neutral approach to the systems we work on. So if you're working with Ruby, simplecov or rcov are going to be your friends, depending on which version of Ruby you're using. Python, coverage.py is one of the best ways to get that collection. C# and .NET, there's a lot of choice. .cover, InCover, OpenCover, all really good tools for doing this collection. There are others as well. In the Java world, you've got Clover, JCov, JCoco, OpenClover, Kobatura. Java's definitely got a lot of choice in this space. And then in JavaScript, both Istanbul and Jest can give you this information as well. Complexity, static analysis tool, such as SonarQube, which is on that list. My favorite for Ruby are Rubocop and Flog, Python, Radon. If you're using C#.NET, Visual Studio has good built-in support for this. There's also a really good tool called Independ in the .NET world. SonarQube also has really good .NET support. SonarQube's also got really good Java support. And there are other Java tools as well. For JavaScript, ESLint and JSHint or CCMJ, if you want a much more lightweight approach to collecting that metric for in the JavaScript world. So that's a quick overview of the different metrics and how we collect them, what they are. But why the focus on these particular 3 metrics? Sorry. So churn. The reason I like to focus on churn is that it allows you to kind of make some inferences about that code that's changed in the past is more likely to change in the future. And it can be a really good stand-in for the single responsibility principle and the open close principle, which are good object-oriented design strategies. You're going to have a pretty one file is going to stand out and change more often if that file always has to change every time you add a feature. So the ultimate goal of a system design would be if you're able to add a feature without having to, the ultimate goal would be to add a feature by just adding a new file to your system. That would be the ultimate goal. If every time you add a feature, there's one file in your system that has to change, then perhaps there's a design smell hidden in that file. And so if it's changing way more often than other files in your system, then that can warrant some further investigation into figuring out why. Code coverage. This is simply that the code that you have under test is going to be safer to change and refactor without there being negative consequences. There's less chance that you're going to introduce a bug. It's much safer to make changes and improvements to code that you already have under test. And the complexity, the more complex the code in your system is, the more danger it is for you to make changes because there's a greater chance that you might introduce a bug. So now we move on to the discussion about what good values are. A lot of controversy here. The ultimate for any of these, what's really important is that your team makes a good decision and that your team agrees on what good values are. What I'm presenting here are definitely my opinions. So churn, in general, low is better, high is not. And recent churn is more important than lifetime churn. You can do some statistical analysis on the churn values and look at maybe 1 or 2 standard deviations in either direction, and that can give you some good insight. This is not churn is not something that I look at all by itself too often. I'm usually looking at it in combination with some of the other metrics to help me kind of pinpoint in the noise that I get from other metrics in terms of where to focus. Code coverage, I consider 100% code coverage across your code base to be asymptotic. But I think 85% is pretty good. And then, like I mentioned before, paying attention to the value that you get from a unit integration and acceptance test, if you can capture those separately from each other, with the idea being that code coverage for unit tests should be higher than integration tests, which should be higher for acceptance tests. Complexity, for cyclomatic complexity, 1 to 5 I consider to be good. This is pretty low for a lot of systems. I know for Radon, which measures cyclomatic complexity in Python, its default is 20. So again, different language communities have different opinions about what's too complex and what's not. I really like really small methods and really small functions that do one thing. And by focusing on a cyclomatic complexity of 1 to 5, that kind of forces me to do that. This is also kind of, when you read the original paper that cyclomatic complexity came from, this is also the rubric that was presented in that paper. So 1 to 5 being good, 6 to 10 being complex, and greater than 10 being too complex and starting to approach that unit of code that's being examined being too complex to analyze. So how do we use these together? This is a spreadsheet that we put together whenever we're working on a code base. So this is an actual client, data from an actual client. We've hidden file names and anything that might give away who this code belongs to. But this is a Ruby project with some JavaScript tossed in. The file at the top is a really interesting one. So the churn value is 1. The complexity count is pretty high. With the complexity count column is how many functions in the file violated are the threshold of 10 that we established, with the max complexity being 72. But if you look at the churn value, the churn is 1. And then when we looked at the file name, we realized that this is a third-party dependency. This is a minified version of a JavaScript library that the team's using. So we're able to completely ignore that. It was only ever checked in once. It's never needed to change. The reason that its complexity scores are ugly is because it's minified, and that's okay. So that's something we're just kind of able to ignore off the top. But if we were only looking at complexity and not looking at some of these other metrics, then that might stand out as a false positive for something we should focus on. The file that is a little more interesting is the next one down. Only 2 methods in that file had a complexity that were greater than the threshold, but one of them topped out at 39. That file's lifetime churn is 27, and its recent churn is 7. So it's changed 7 times in the last 3 months. So 3 months is what we used as the definition of recent churn. And it looks like it's pretty complex. And when we look at coverage, the coverage for that file is just 4%. So that's one that we would definitely strongly encourage the team to narrow in on and take a focus on. One that would be less stressful would be the one on down with the lifetime churn is 38, but the recent churn is 1. Maybe get the laser pointer might help here. There we go. So the lifetime churn is 38, but the recent churn is 1. Coverage is relatively high, so this, if you're having to pick whether or not you put your energy in this file, it hasn't had to change all that recently. It had to change a lot in the past. Complexity is not too bad relative to some of the others, and the coverage is pretty decent. So instead, kind of focusing on some of the others where coverage is low relative to that. So that was a project that was actually doing fairly well. This one's doing much worse. So this is a PHP project, and we can see here that that top file is definitely the one that stands out. A really good kind of eyeball test is red all the way across. It is a really good indicator that focus needs to be paid on it. So we have 13 methods that have violated the complexity threshold. One with a max complexity of 92, and code coverage is 0 across the entire file. And while its lifetime churn is much higher than its recent churn isn't 0. So it's definitely an area of focus. And just looking at this picture overall, we can see that this looks like a project that might be in a little bit of trouble and might need a lot more effort and help than the team that's working on this one. This one, by comparison, is this team is in a much better shape than this team. So with all that kind of in mind, we can start to look at some common scenarios, which I've kind of teased a little bit at already. So if we consider that like low versus high are the values that we plug into these boxes for complexity, code coverage, and churn, any ideas what a healthy code base might look like? Any volunteers to shout that out? Okay, I'll give it away. So low complexity, high code coverage, and low churn. Like that's just a decent general metric for what a healthy code base looks like when you're comparing these 3 metrics together. So any ideas what a code base might look like if it's got some design smells in it? High complexity, low coverage? High churn. Yep. So complexity is being managed pretty well. Code coverage is being managed well, but the churn's high. So this could be a team that's doing a good job managing the complexity. They're doing a good job keeping the code that they're writing covered, but they've got some files that really have unusual churn. So that could be an indication that the way they've architected their system isn't working for them all that well, and so that can be an area of improvement for them. So what would a team where testing isn't necessarily a focus for them look like? What kind of comparing these 3 might look like? Low code coverage, yeah. So that was kind of easy. So the team's in this case, the team's doing a good job managing the complexity. They're keeping complexity low. Their churn indicates that the churn values indicate that they don't really necessarily have any design smells lurking in the code base, but code coverage is low. So in this case, that might not be all that important. Like if the team is managing complexity, and it's well factored and well designed, then increasing that code coverage might be less of a priority for this team than just continuing to do really good on the other things that they're doing. And then on a team where factoring isn't a focus, what that might look like. If anybody's noticing pattern, that kind of gives it away. So if complexity is really high, than a team that kind of has this characteristic. They're not concerned with refactoring. They may be doing a really good job with coverage. They may be doing, that their design is set up in such a way that they're able to add new files and to kind of manage the way that their application is structured, so that churn doesn't get out of hand. But complexity is pretty high. So then, a more complicated scenario is a code base where it's kind of unhealthy but less of a priority. Any ideas what this might look like? Okay. So complexity is high, code coverage is low, but churn is low. So in this case, this is a little subtle. There's another law, another set of laws for software development called Layman's laws, and these talk about how entropy can kind of play a factor in the software systems we work on. And one of the conclusions that you can draw from Layman's laws is that any software system that's used is going to have a strong pressure on it to change. So the only software systems that aren't going to need to change are the ones that aren't being used anymore. So in this scenario, if churn across the entire code base is low, but these other metrics are high, then perhaps this isn't a system that's worth working on. So there have been some systems that we've come in and we've taken a peek at, and we've set our threshold for recent churn to be 3 months, and the entire column was zeroed out, which means that for that system, not a single file in the system had changed in 3 months. So in that scenario, do any of the other metrics really matter? It's worth considering that perhaps this system isn't being used anymore, or there could be another reason. It could just be that it's been completely ignored. So that can be an indication that this system either shouldn't be a priority in the future, or that's a symptom that it hasn't been a priority in the past. So that can kind of glean some insights there. So unhealthy but a high priority is when you've got high all across. When they're not high all across the board, but when they're kind of in the red all across the board. So complexity is high, code coverage is low, churn is high. This is a software system that's in trouble, or this is a file that's in trouble and really kind of needs attention and stands out as a hotspot. So I always like to run through my material pretty quickly so I can facilitate some sort of discussion. We've got about 7.5 minutes left if anybody has any questions. All right. Did I see a?
So I do have a legacy system that I've just started maintaining. So my question is, are there any tools like this for Perl?
For Perl, yeah. So there are cyclomatic complexity analysis tools that you can get for Perl. There are code coverage analysis tools that you can get for Perl. And then what source control system are you using?
We're using Git.
Git. Okay. Yeah. Then yeah. So you can get all three of these data points for Perl.
So before I start refactoring it might be a good idea to understand it a little bit better.
Another good resource for Perl, if you're looking for a good Perl resource, there's a book called The Perl Medic.
Okay.
That I definitely suggest adding to your toolbox. It takes a kind of a health metaphor approach to refactoring Perl and upgrading Perl versions to more modern Perl versions.
All right. Thanks.
Yep. Any other questions? Well, awesome.
All right.
I appreciate your time, and I guess you can go try to squeeze in a few minutes out of the next open space.
Yeah. Hey, thanks so much. Great job. Let's give him a hand.